Echo. Dim little lamp.
Okay.
You're supposed to dim it. Fucking what? My pen. It's too bright. Right, so let's get into it then, and then I'll put this on the playlist, the GCSE playlist for people. So circuits is something kids do seem to struggle with at GCSE. So this is what I'm going to cover. I'm going to cover the definitions of current, voltage, and resistance. Again, for GCSE level, series and parallel circuits, Ohm's law, how to use it, how to rearrange the equation, ohmic conductors, what an ohmic conductor is, and the graphs needed for ohmic conductors. And then this is sort of the higher level stuff over here. How we create, using LDRs and thermistors, a circuit that will detect changes in light and temperature level. So, yeah. Oh, yeah, and then afterwards, I'm doing about 4 o'clock today. For anyone who's interested, I'm doing a hangout on here, live hangout with Sean Hawkins, if I can figure out how to do one of those. Right, so let's begin. Oh, my phone's buzzing. Come on. Right. So, current, voltage, and resistance. What do you need to know if you're about to sit your exam? Well, a lot of people get confused about the terminology surrounding current, voltage, and resistance, and they talk about voltage moving through a circuit, and you know, let's make sure we tighten that up to start with. I like to use an analogy, and that's all this is. It's just an analogy, but it's one that will see you through your GCSE exams. I want to imagine that this is a racetrack, essentially, and that this is where my cars start and finish. Let's say I've got 10 cars leaving this point here. If those cars were to drive around this track, all of those cars would make it back to this starting point here. If I had 11 cars, then all those 11 cars would move past. And I like to think of electric current being a little bit like that. There is a significant difference, which we'll talk about later on. But if we just imagine it as the number of things that are moving around the track. Now, what are those things moving around the track in circuits? Well, they are electrons. If you don't know your atomic structure, electrons are the negatively charged particles that spin around the nucleus. They will leave the battery, they will go around the circuit, and they'll go back to the battery or to the cell. Now, what they won't do is they won't get used up by the bulb that's here. So if I have 10 electrons leaving here and traveling all the way around, I will have 10 electrons either side of the bulb. All right. If I was stood here watching the race, right, I would see just as many cars pass or electrons pass as if I was stood here watching the race that way. So how do I put that into a definition? Well, it's the flow of electrons. And I can say that. I can say the flow of electrons. That's not a problem. I'd pick that up on the mark scheme. But electrons are those charged particles. So what they really want on the mark scheme is the flow of charge. So it's how many are actually moving. Now, we are going to use this analogy of cars going around a track, but just for that deeper understanding, I just want you to know that when the electrons move, it's not a case that they start here and, let's say if there was 2 bulbs in the circuit, they see this bulb first and then they meet that bulb second. It's a little bit more like water in a pipe. So if this was filled with water, all the water would move at the same time. So there is no first, there's no second, right? A lot of people get confused about, well, why hasn't this bulb used up all the current? How do the or the voltage, how do the electrons know to save some voltage, etc.? They do all move together like water in a pipe. But this is a good analogy to start with. So your first definition, it is the flow of electrons or the flow of charge. Voltage would be my second definition that we need to know. Now, you'll hear voltage described as the work done per unit charge or the joules per coulomb. That's fine. GCSE level, this is the best analogy I can give. These electrons can't go anywhere unless they have energy. It's like me or you. We can't go anywhere unless there's some sort of, unless we've got some sort of energy from somewhere. And the voltage is the energy that they're given by the battery. So it is literally the energy they need to go around the circuit. So that is the voltage. Resistance. oh, sorry, the definition for voltage. We are going to use the definition, the work done, which means the energy the electrons have per unit charge, which means per electron. So it's really the energy each electron has, work done per unit charge. You need to know this definition off by heart, okay? Now, resistance, these electrons leave here with, and this is going to look a little bit daft, but they leave here with loads of energy. So they're really happy, they're jumping around, they've got lots and lots and lots of energy. But then they get to this first bulb, and this first bulb, imagine it like a roundabout the cars have got to go around. And I don't want to use the term slow down, but let's imagine that it's not as easy for the electrons to go through this bulb as it is for them to go through the wire. It's not as easy for them to get around the roundabout. So they struggle to get through that, and they have to use energy to get through it. So the voltage they're given by the cell, they have to use when they pass through this bulb, and this bulb as well. All right, they have to use every time they get through, get to any component, they have to use some of that voltage. Now, at a higher level, you'll know they have to also use some voltage just to get through the wires, or even the cell itself when you're looking at internal resistance. But that's not in the GCSE specification. All GCSE pupils need to know is that this voltage here, or the energy, right, this 10 volts given to the electrons, will be split or used by these two bulbs. So let's look at some practical examples of that. First of all, how do I measure them? This is my symbol for an ammeter. An ammeter is what we use to measure electrical current, and we measure electrical current in amps. So that's what the ammeter is for. The voltmeter, we measure in volts. Now notice how I've connected the voltmeter around the bulb. This is called connecting something in parallel. So when we look at series and parallel circuits in a minute, hopefully, oh, I need to turn those notifications off. Hopefully this will make sense. All right. A voltmeter is always connected in parallel. An ammeter is always connected as part of the loop. We say that's connected in series if you're part of the loop. Now, a voltmeter, in case you're asked, has to have an incredibly high resistance, a really massive resistance. And the reason is when the electrons get here, if I want to measure the voltage across here, what I don't want is electrons choosing to go through the voltmeter itself, because therefore, just by putting the voltmeter in the circuit, I'm going to affect the results. All right, by trying to measure it, I'm actually going to affect the circuit. So this has a very high resistance, makes it very difficult for that current, that flow of charge to travel through. You may, at this point, I'm going to introduce the term potential difference. Now, you may get confused between potential difference and voltage, but don't, because at GCSE level, all we are concerned about is that they're the same thing. All right. You will have heard of potential energy, chemical potential energy, gravitational potential energy, elastic potential energy. Right? We talked about voltage being the energy the electrons have. So when I measure the potential difference, I'm measuring the difference in energy that this electron has here when it enters the bulb, and I'm comparing it to the energy this electron has here when it's left the bulb. That's why we get the term potential difference. Right. So what have we done? Have we got a definition for current? Yeah, flow of charge. Have we got a definition for voltage? Yeah, we imagine it as the energy carried by the electrons. It's the work done per unit charge. It's the energy needed to push an electron through a component. And resistance is opposition to current flow. Right? If I increase the resistance, I make it harder for the current to flow. And we measure that in ohms. You may see this weird symbol, right, on your exam. That weird symbol there. That is also acceptable instead of writing ohms. So how are series and parallel circuits different? Well, let's have a look. This is going to get a little bit higher. Those people that know circuits quite well and know about potential dividers, we're kind of almost touching on that here. So let's say I've got a circuit, and again, I'm just going to use 12 volts, my battery. So this, or my cell, sorry. By the way, the difference between a cell and a battery for you guys, a cell is just one of these components. A battery is multiple put together. It's a battery of cells. Okay, so here I've got 1, 2, 3 cells. Now, what they might try and catch you out with is, are the cells put in the right way? So these 3 cells here are all facing the same way. So like the long line here is on the right-hand side for each cell. If each cell here was 1.5 volts, then putting these 3 together, I would just add the 1.5 to 1.5 to 1.5, and I'd have a 4.5 volt battery. what they might try and do is catch you out by doing something like this. And if you notice here, this middle cell is, let's move that lamp. This middle cell here is the wrong way around. The total voltage of this is going to be this 1.5 minus the 1.5 here, plus the 1.5 there. So actually the total voltage there is just going to be 1.5 volts. Anyway, scrap that, back to the circuit. So I've got 12 volts here, and I have two resistors. Now, if these two resistors had exactly the same resistance, so let's say this is a 6 ohm resistor and this is a 6 ohm resistor, or it could be 3 and 3 or 2 and 2 or 1 and 1, whatever. Then the energy needed to get through each resistor will be the same. The energy the electrons needed will be the same, which means that this voltage will be equally split between these two components. So 6 volts for this one and 6 volts for that. But resistance and the voltage a component takes are linked. What do I mean by that? Well, let's say this has a resistance of 12 ohms, twice as big as this, right? That resistance is twice as much. Then for this circuit, it's going to take twice as much energy for the electrons to pass through this resistor than that one. So they take twice as much voltage, right? They will take 8 volts here, and this will only take 4 volts in this situation. It's like a ratio. When you get to A level and you do potential dividers, you use this a lot, and we're going to be using this idea when we do the light and temperature sensing circuits later on. If I was to put an ammeter in this circuit, if this ammeter here said 4 amps, right, and it wouldn't with those resistances, would it? But let's just say it says 4 amps, then I could put another ammeter anywhere I want in the circuit, and remember it would also say 4 amps, all right? That's a series circuit. Parallel circuits are a little bit different. This time I'm going to take my 12 volt battery, and we're going to assume that all of these resistors have the same resistance. And I've just chucked a bulb in here as well, just to show that sometimes I use bulbs and not resistors. We don't have to be worried about the type of question we're going to get. As long as it's a component, it will work. It doesn't matter whether it's a bulb, a buzzer, an LED, or what. Right. So a lot of people take the idea of the voltage splitting in a series circuit, and when we're given a parallel circuit, they'd say, oh, right, I've got 1, 2, 3, 4, 5 components, therefore I'm going to divide my 12 volts by 5, and that'll be the voltage against each. But no. All right. Those of you who've done A-level and know about Kirchhoff's first and second law, I'm not going to use that terminology here, but essentially, in a parallel circuit, we treat each branch as a completely separate standalone circuit, a completely separate standalone loop. So this 12 volts here will be given to this entire branch. This entire branch will have 12 volts. This entire branch will have 12 volts. This branch here will have 12 volts, and we treat them as separate series circuits. So the voltage across this resistor, if these two have the same resistances, well, that'll be 6 volts and that'll be 6 volts. You know, if these two had the same resistance, that'd be 6 and that'd be 6. If this was twice as big, so let's say this is R and this is 2R, then this would take twice as much voltage. So that would be 8 volts, and this would be 4 volts, and this bulb here would take 12 volts. So what about current? Right. Again, some people may remember the term Kirchhoff's first law. We are not getting into it that deep. And again, I'm making up, it wouldn't be 10 amps with these resistances, so we'll just get short of those. But let's say I have 10 amps leaving this circuit here. Leaving the cell here. Then this 10 amps would have to come back to that cell. So if I had an ammeter somewhere over here at this point, that would also measure 10 amps. But the current here has a choice. It may choose to go this way when it's at this junction, or it may carry on. When it gets to this junction, it may choose to go that way, or it may carry on. So it's, and end up going this way. So essentially the current that leaves the cell will split between the 3 branches. Now it won't split evenly between the 3 branches. If this branch has a resistance of, let's say, 2R, and this branch has a resistance of R, then this will have much less current going through it than this one. In fact, to make it simple, if we got rid of the bottom branch altogether, then if the resistance of this was twice as big, it would have half as much current going through it as that one. So the resistance of each branch will determine how much current each branch gets. Yeah. Just lost myself there for a second. Yeah, so the take-home point for that is in a parallel circuit, the voltage of the cell is given to each branch. That's why when you're in school and you start putting bulbs together like this in a parallel circuit, the bulbs stay the same brightness. They don't get dimmer like they would if you added them in a loop in a series circuit, because each of them is getting the full voltage from the battery. So how do I apply all of that in some questions? Where are we up to now? We've done a brief look at series and parallel circuits. Yeah, Ohm's law. Yeah, number 3, Ohm's law. So Ohm's law, as far as we are concerned at GCSE, is at the minute just an equation, and the equation is given us by V equals I times R. Voltage equals current times resistance. We don't use the letter C for current. C in your circuits would stand for coulombs, which is the unit of charge. I don't know if anyone knows in the chat why we use the letter I. I'd be fascinated. I've no idea why I is the letter that we actually use. But voltage equals current times resistance. That is known as Ohm's law formula, or the Ohm's law equation. We'll get a little bit deeper into that later on. So what kind of question, excuse me, what kind of question might you get? You might be asked to calculate, for example, the resistance of this bulb right here. So how do I use this equation? Well, first of all, I need to rearrange it to find resistance. So R would be V over I. For anybody struggling, for anyone who's struggling on how to rearrange an equation, let me just give you this tip. Remember, if I have an equation that is something equals something times something, then I can put them into my equation triangle, which looks like this. An equation triangle has a divide in the middle, it has a multiplication at the bottom. And then I put my letters in, but whatever goes here, right, if it's something equals something times something, whatever goes here will always go at the top of the triangle. The I and the R would then go at the bottom. And then I simply cover up the thing I want to know. So if I can't rearrange my equation, but I want to know what resistance is, if I cover up resistance, then that box, that triangle now tells me voltage divided by current. If I want to know what current is, cover that up, it tells me voltage divided by resistance. And if I want to know voltage, obviously I cover those up, current times resistance. That's if I have an equation that looks like that. But if I was given it like this, R equals V over I, and I wanted to put that in a triangle, well, this is a different type of equation. If I have something on top, whatever is on top stays on top in the triangle, which will give me this exact same triangle again, obviously, because this is a triangle that works out. So that's how you put your own equations in triangles to help yourself rearrange them. So anyway, back to the question. I want to work out the resistance of this bulb. So I use my triangle, or I just use my knowledge of rearranging equations to know that it's voltage divided by current. So what is the voltage of this bulb here? Well, if I've got a supply voltage of 12 volts, again, we ignore lost volts and internal resistance in the battery. None of that is important at GCSE. We just assume that this 12 volts is split between these two bulbs. I'm given that, so this must be 4 volts. So R equals V over I, resistance equals 4 divided by, well, it says here that my current is 2 amps. Now remember, in a series circuit, that current will be the same all the way around. So 4 divided by 2 gives me 2 ohms. Let's make that much more difficult. Oops, passed that one. Oh no, where's my sheet? Let's make this much more difficult now. So these are bulbs I'm drawing. Let's say I've got a 12 volt cell, and I know that this has a resistance of R. This has a resistance of 2R. I know that the current here is, let's just say 10 amps. And I know that going through here, I have, should have planned this one out earlier on. Let's say going through here, I have 4 amps. So my question would be, can I work out the resistance of each of these bulbs? Okay, well, the first thing I'm going to do, so this is much higher level question. Can I tell you what this resistor is and what this was, the resistance of that and the resistance of that is? I know that this is twice the resistance of that. Okay, but what are the individual resistances? Well, I'm going to go back to my Ohm's law. R equals V over I. I've rearranged that. So what do I need to know? I need to know the voltage and I need to know the current. Well, how do I figure out the voltage? I learn my rules of voltage for series and parallel circuits, and I know that this branch will have a voltage of 12 volts across it. So what I'm going to do is I'm going to work out the resistance of the entire branch to start with. 12 divided by, what's my current going to be? Well, I remember what we learned about current. If I've got 10 amps leaving the cell and 4 amps are going down here, there must be 6 amps along here. So 12 divided by 6. What does that give me? That gives me 2. So I know that the resistance of this entire branch is 2 ohms. So what's the resistance of each of these? Well, 2 ohms shared between these two resistors. I know that this has half the resistance of that. In total, how many R's have I got? I've got 2 plus 1. I've actually got 3 like blocks of resistance, if you like. This has 2, that has 1. So if I divide my 2 by 3, which obviously gives me 2/3, then I know that this has a resistance of 2/3, right? Or 0.6, and this has a resistance of twice that, 4/3, okay, which is, that's 0.6 reoccurring. What is going on with my brain here? 1.2. Why can't I add that over my head? It's the pressure of being on a live stream. How about that? Right. But what I would do is I would calculate the resistance of the entire branch. And then this would have to have half the resistance of that. So that's a tricky one for Gcse level anyway. Ohmic conductors. We said Ohm's law is V equals I times R, but that's the Ohm's law equation. But what does Ohm's law itself actually state? Well, for a normal component, if I have, let's say, this resistor here, and the temperature of that resistance isn't changing, we'll talk about why that's important later on. If that resistor is what we call fixed, and the resistance doesn't change, that means if I increase the voltage, the current will increase. In fact, if I double the voltage, the current will double. If I treble the voltage, the current will treble. And that will give me a graph that looks like this. As I increase the voltage, I get a straight line. This is what Ohm's law states, right? Ohm's law states that voltage and current are directly proportional. So if something is obeying Ohm's law, this is going on inside it. Now, that will only happen when we look at a resistor if the temperature stays the same. And the reason being is this, right? And quite often we are asked about resistance and temperature. So let's have a look at the keywords. Why does the temperature affect a resistor, for example? Well, what is current? It's the movement, it's the flow of electrons. We've talked about that. So if current is the flow of electrons, then what are those electrons moving through? Essentially, they're having to move in between the gaps between the particles or the nuclei in the metal. They're having to do that with the resistor. And if the temperature increases, what happens is the particles, or we call it the lattice, which is like the pattern that particles make, the lattice will start to vibrate more. And it's fine to say the particles will vibrate more. So they start to move around. And if you're an electron trying to get through that resistor and all the particles are moving around like this, you're going to bang into them. It's like trying to walk down a corridor, right? And at cold temperature, everybody stood still. You can just find your path and you can walk down it. But then when you're walking down the corridor and everyone's running around, it's going to scupper things for you. So, resistance is the flow of electrons. If I increase the temperature, the lattice will vibrate more, and that causes more collisions. And those collisions lead to friction and electrical energy being lost as heat. So just get that train of sort of keywords for any kind of question about temperature and resistance, and we'll see one in a minute, right? So why does temperature increase resistance? Because current is the flow of electrons, but as the temperature increases, the lattice vibrates, or the particles inside the conductor vibrate more. This causes more collisions between the electrons and the particles, and the resulting friction causes a loss of energy as heat. Right. Anyway, there are 3 graphs you've got to know on your GCSE paper that are Ohm's law graphs. And you're quite often asked, how would I collect the data to make these graphs? So this where we're up to, just as a reminder. So this is where we are. We're almost done. After we've done the ohmic conductors bit, we'll do the hard question down here, and then we'll call it a day. I don't know how long this stream's been on for, but I'm going to keep them short. Short and sweet. And boring. Desperately boring. Right. So if I take a circuit and I put a gap in that circuit, and I place my voltmeter around here, then anything I put in this gap here, I can measure the current going through it, and I can measure the voltage across it, or the potential difference across it. There are three components you need to know. You need to know the resistor, and right at the very end I will just put the circuit components that you need to know and give you a quick bit about them. So this is just a resistor, but we call it a fixed resistor. A fixed resistor, sorry, just give me a second. A fixed resistor basically means it's not going to change its resistance. So I could put that in that gap. I could put a diode in the gap. Now, a diode, well, in fact, we'll come to that later on. Or I could put a bulb in the gap, and they might call the bulb a filament lamp. So like a bulb that's got a wire in a filament that gets hot and glows. If I put them in the gap, and then I start to increase the voltage here, I'm going to get different voltmeter readings and different current readings, and I can then draw a graph. And you have to know the shape of those graphs, and you have to be able to explain the shape of those graphs. Let's take the fixed resistor at a constant temperature. We've said it obeys Ohm's law, it's an ohmic conductor. But if I then took that power supply and turned it around, so I switched the battery the other way around, then on your ammeter, you might get, and I get this in school a lot, why does it say minus on my ammeter? Really, it's just telling you that the electrons are flowing in a different direction. Think about it like that. I can plot the negative direction. So in other words, I've got a clockwise, think of it as clockwise and anti-clockwise, and I get the same movement. So why does a fixed resistor take this? Because it obeys, take the shape, sorry, because it obeys Ohm's law. Voltage and current are always proportional. But what if I put, let's do this next. Let's do the bulb. If I put a bulb in this gap, I'm going to get something different. With a bulb, it starts off obeying Ohm's law. So here's current, here's voltage. It will start off as the voltage increases, the current proportionally increasing. But what happens to a bulb as it gets brighter, or shortly after you've turned it on? It starts to get hotter. So around about here, when there's enough current going through, the temperature, or the increase in temperature, is causing, or is actually being caused by those collisions and that friction, because those particles are vibrating more, and essentially the resistance is increasing. So around right here, because the resistance is increasing, I need a bigger jump in voltage to get the same jump in current. It's harder for me to increase my current as much if the resistance is higher. So the graph tails off. It doesn't go perfectly flat. Maybe that looks a bit flatter than I should have done it. And I would have got the same result if I'd turned the battery around and done it in the opposite direction. So I get like this S shape. But you have to be able to explain what's going on up here. An increase in temperature causing an increase in collisions between the electrons and the particles, because the particles in the filament are vibrating more. And that is what causes increasing resistance. So I get a smaller increase in current. That's key. Diode. Let's look at the diode. Now, first of all, what does a diode do? We can't understand the diode graph unless we know what a diode actually does. I like to see the diode as being an arrow. Yeah, this arrow is pointing that way. And this tells me that it will only let current, and when I say current, I mean conventional current, not electron flow. This is more of an A-level idea, but there will be people out there that understand that conventional current and the direction of flow of electrons are actually opposite. To cut a long story short, think about it like this. When people started faffing about with circuits, they didn't realize that it was electrons that went from the negative to the positive. And all the circuitry was based on a flow of positive to negative. So when we talk about conventional current, it's actually opposite to electron flow. Anyway, a diode, we look as like a one-way door. The current will flow in one direction where the arrow points, but if you try and go in the other direction, you're hit by this brick wall here and you can't get through. That's a diode. If I put these two arrows on, it's now a light emitting diode. So if you're learning your circuit symbols, these two arrows mean light emitting. And as we'll see in a minute, if we drew the arrows towards something, that would mean light dependent. Just throw that in there for now. So what would the graph look like for this? Well, a diode will not let electricity flow backwards. So we're not going to get any current really in this negative direction to draw it on the exam, we draw it very, very close to that x-axis. Now, once we get past this central point here, and we're now in the positive direction, it will allow current to flow, but we have to make sure that we're now away from the negative numbers. So you see it kind of, I've joined it to this central section here, but it doesn't allow current to flow straight away. There's a tiny switch on voltage, usually around about 0.6 volts for the questions you need. And when we hit that 0.6 volts, it will shoot off. So a diode is by far the hardest of them to explain. Here, it is obeying Ohm's law. Voltage and current are proportional. Here, well, it's a straight line at least. But this bit is the bit you've got to remember. Okay, and the reason it doesn't go down on this side is because it will only let electricity flow in one direction. Right, let's get to the culmination of all of this, which is how do I use the following components, right? I know you know that's a resistor. If I put a tick on it, it suddenly becomes a special type of resistor. It becomes a thermistor. How do I use a thermistor, which is a resistor that changes with temperature, or this type of resistor, which has, can you guess what we said before? The arrows are pointing towards it. So this is a light dependent resistor or an LDR. How do I create those or use those to create a circuit that will detect changes in temperature and give me a reading so I can actually make a light meter or a temperature sensor? This is a circuit that you are going to need to learn. Now, one of these resistors is a fixed resistor. Let's just say it's this one. This one here can be any one of these. I'm going to make it a thermistor for now. Now, before we get any further, we have to know the characteristics of a thermistor and the characteristics of an LDR. And you have to know this graph. Resistance, if this is an LDR, then we'll have light intensity on the x-axis. If I'm doing it for a thermistor, I'll have temperature on the x-axis, but the shape of the graph is the same no matter what. Imagine it like it's not a half-life graph, but imagine it like the half-life graph you do for radioactivity. Essentially, what do you need to know? That as the light or the temperature increases, the resistance decreases. So how do I use that to answer that high level question at the end, or when I say high level, it's sort of like, level 7, level 8 question on how do I make a temperature or light sensing circuit? Well, let's think about what we know. If this is a 12 volt cell, then I know that the voltage of this and the voltage of this will add up to 12 volts. Again, we're ignoring lost volts in the battery and voltage used for the wires. That's not important at Gcse. So this plus this will equal 12 volts. Now, this is the thermistor whose resistance is temperature dependent. Let's just say, I'm plucking this out of thin air, let's just say the resistance of that now, keep the numbers simple, is 6 ohms. This is our fixed resistor. That is 6 ohms. That's never going to change because it's a fixed resistor. That is 6 ohms. Now, at the minute, the voltage across this and the voltage across that are going to be the same because they have the same resistance. It takes the electrons the same energy to pass through them. And because our voltage is 12, if they have the same resistance, they'd actually have 6 volts each as well. Now imagine I take 2 wires and I put them here. If I know there's 6 volts here, then actually, if I put a voltmeter there, that voltmeter is going to read 6 volts. That's what it's going to say. Obviously, because that's a 6 volt resistor. But then I start to change the temperature. If the temperature starts to go up, the resistance of this is going to drop. So now maybe the resistance of that has dropped to 3. And what have we got? The resistance of that is half as big as that. In other words, this now needs less energy for the electrons to pass through it than this. And it needs half as much energy for the electrons to pass through as this. And that's reflected in the voltage. Because as the resistance of that drops, the voltage needed drops. And now, I mean, simple, you won't be asked to work out the ratios, but a simple ratio, this is a 1 to 2. This will probably need about 4 volts. This will need about 8 volts. The only reason this has gone up is because these two still have to equal 12, right? But this has gone down because its resistance has gone down. So what will happen if the voltage of that goes down and the voltage of that goes up? What's going to happen to this reading here? The needle on that voltmeter is going to go up. So if I've got a nice little scale on my voltmeter that tells me instead of having volts on it, has got degrees C and it's all perfectly calibrated, then as the temperature goes up and the voltage of this goes down and the voltage of that goes up, that needle reading can tell me how much the temperature has gone up. Let me give you the key words that you need to answer this question, and then we'll talk about the LDR very quickly. Right, so the key things we have to say is, as the temperature increases, right, that has to be in there, the resistance of the thermistor decreases. If the resistance of the thermistor decreases, the voltage across the thermistor has to decrease. And if the voltage across that decreases, then the fixed resistor voltage must increase. And the fixed resistor voltage must increase because the total voltage of these two must equal the supply voltage, which is a 12. And that's simply it. These are the key points that you need to include. If I was using an LDR, it would be exactly the same. All of this will be the same, except wherever I use the word temperature, I'd use the word light intensity, or I'd just use the term light. Okay, I'll have a look at the chat in a minute to see if there's any questions. This will be really basic for a lot of people, but it is just GCSE, really. The circuit symbols you need to know, let's just fly through those, and then we'll see what questions there are in the chat. So the circuit symbols are, that's your cell. Battery, remember, is just as long as you've got more than one cell put together, you need to know that. You need to know your ammeter, which we connect in series. You need to know your voltmeter, which is connected in parallel. You need to know your fixed resistor, which is that one. We need to know a variable resistor, which is like a dimmer switch. Think of it like a dimmer switch, which is a resistor with an arrow going through. We've already talked about the thermistor, which has a tick. It's a resistor that we've just done with temperature. We've got the LDR you need to know, which is this one. We've talked about the diode. You need to know the diode. Remember, that allows current to flow through in one direction. If I put the two arrows on the diode, then it becomes a light emitting diode. You need to know that one. A fuse. We need to know this. Now, there's loads more. We've got static electricity to talk about. We've got fuses and plugs and how a earth wire works and protects protection devices. Why some countries don't have an earth wire. Blah 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 blah. But that is just a short, concise thing to get you up to speed with the circuit rules. So I'm going to call that a day there. Just before I get to the chat, see if there are any questions on this. Just a reminder that later on today, I think we agreed 4 o'clock UK time, but I'm going to get in touch with him and ask. Sean Hawkins will be having a chat with me on here if I can figure out how to get the Hangouts and OBS to work. But I think he's a master at that. I'm sure he'll be able to help me out. So that's a 4. Oh, he's in the chat now. Hi, Sean. Right. Have I got any... Well, if you've got any questions on this, just pump it out now, and I'll answer them. Will this be put out as a standalone video? But this is going to... ISI. This is just going to stay up, and I'm going to put it in the GCSE revision playlist. The idea is I'm going to do one of these, at least one of these a week. They'll always be at 1 o'clock on a Sunday afternoon, and then by the time GCSE exams come around, anyone with any kids can just direct them to the playlist, and everything will be there for the entire course. So it's not really about views, this, because it's going to be quite boring, but it's just hopefully a resource that can stay up there. Let's have a look. Nobody mentioned Zener diodes. I'll be honest, I don't even know what a Zener diode is. I've never... All right, okay. Tom K. Fly. Ohm's law is often shown as E equals I over R, where equals electromotive force. Yeah, so if you hear the term EMF, then essentially that is the voltage of the cell before it's had to overcome its internal resistance, before it's lost volts for that. I think, do the Ohm's law triangle. What now? So the Ohm's law triangle is V, I, R. There you go. Right. I think I'm just going to bore people now because I haven't got anything entertaining to say at all. But I'll wait until, I'll save that till Sean's on later on. Sean, I'm looking forward to the chat later on. And yeah, feel free to pass the link on to the kids once it's processed. I'll put it in a playlist and I will see you all another time. Bye-bye.